Hello, linear algebra student. This video is for chapter 4.4, part 3. We're continuing with using coordinate vector to determine if a vector space of polynomials are linear dependence, or like some sets of polynomials are linear dependence in polynomial of degree 2. And then if they are dependent, write one polynomial as a linear combination of the other. By definition, these sets can be written as columns of a vectors of their coefficient. So coefficient of 1, coefficient of t, and coefficient of t squared. So that's how we form this. So t negative t squared becomes 0, 1, negative 1, etc. And to determine dependence, we would have to determine if these vectors are dependent. That is to solve Ax equal to 0, right? So this is how we solve it by doing an augmented matrix of 0, negative 1, 2, 7, negative 3, 1, 5, negative 1, 0, 0, 0. And I have put it in here, the augmented matrix of solving Ax equal to 0. If I do a row echelon of A, it is solvable as 1, 0, negative 0.5. So there is only two prefix position. So it would be solving as REF is not 0, 0, 0, but 1, 0, negative 0.5, 0, 0, 1.5, 0, and 0, 0, 0, 0. So that means the way that we make that equal to 0 is x1 is equal to x1, x2, x3, right? 1/2 of x3, x2 plus 1/2 of x3 equal to 0. That means it's negative 1/2 of x3, and x3 is free. Meaning x1, x2, x3, which is the linear combination of the vectors equal to 0, can be solved as x3, 1/2, negative 1/2, and 1. So how can I write linear combination? So when x is 3 is 1, then we would have one of the solution would be what? 1/2, negative 1/2, and 1. So we can write, let's call this P1, the second one P2, the third is P3. Then we would have 1/2 P1 minus 1/2 P2 plus 1 times P3 equal to 0. So that is the dependent relationship. And so we can write P3 is equal to negative 1/2 of P1 plus 1/2 of P2. Or to write it better, 1 plus 3t minus t squared is actually negative 1/2 of P1 is t minus t squared plus 1/2 of 2 plus 7t minus 3t squared. So we can casually check that it is right. So if I do the constant term is 1/2 times 2 is 1. Negative 1/2 t plus 7 over t is 3t. Yeah. So example 2, use the coordinate vector to determine this set is a basis. So let's use coordinate vector to make this set. This set is actually equivalent to a set of vector of 1, negative 1, negative, no, 1, 0, because there's no t here. Negative 1, 0, 1, negative 1. Oh, this is one vector. This is another vector. And then the third vector is 2, negative 2, 1. Okay, so it is equivalent of this in R3. So to check if this is a base, is to check if this is a base, that means I'm going to put them in column. And then check if this vector can be, this matrix can be converted into a identity matrix using the inverse matrix theorem. 1, 0, -1, 0, 0, +1, -1, 2. Okay, so we do a row echelon of B. Oh, we did an identity matrix, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. Hands by IMT, which is very good. These the vectors are dependent? No, independent. As well as span out 3. And by the isomorphism, the polynomials bases independence also span P2. Hence, a basis for P2. We want to find a coordinate vectors of 3 plus t minus 6t squared. So that is to solve the equation. 3, 1, -6 equal to P of B, which is 1, 0, -1, 6, 1, -1, 2, -2, 1 times your x1, x2, x3 under the new base, right? So this is to solve, so use the augmented matrix of 1, 0, -1, 6, 1, -1, 2, -2, 1, and then 3, 1, -6. RREF it, which I have. 1, 0, -1, 0. How come I say 0? Oh, I don't say 6. It should be 0. Yeah, 0. 0, 1, -1, 2, -2, 3, 1, 6. And I have it already, so I just need to do REF it to solve. So the answer is 7, -3 and 2. 1, 0, 0, 7, -3 and 2. So 1, 0, 0, 0, 1. So that should always be one answer. So XB is equal to 7, -3, 2. So this is the coordinate vector of the P of T. Is the coordinate vector. For P of T. Okay, so the last things I want to okay, so then we would have 2 more example on polynomial. This is to find a set that span Pn and a basis for Pn. So determine if this span P2. I think it is similar to example 2, right? To see if it span P2, we use the coordinate vector. So we write the vector as, so this set, let's say this set is equal to C, or yeah, let's say C. C would be isomorphic to a vector 0, 5, 1, 5, 1, comma 1, -8, -2, comma -3, 4, 2, right? Just get all the coefficient. And also there's a fourth one, 2, -3, 0, right? Because there's no t square. So can they span P2? I have 4 of them. They're more than enough, right? So maybe 3 of them can. So that should be one left over. So what we can do is just put them into a matrix, right? As 0, 5, 1, 1, -8, -2, -3, 4, 2, 2, -3, 0, and then see if they are dependent, right? So see if I can have um, for you to span it, I have to have perfect position in all rows. So see if it's possible. So do the augmentics and do RREF. So see what I have. So I have it here written 0, 5, 1, 1, negative 8, negative 2, right? So and then 0, 0, 0. So it's in D. I do a reduce row echelon of D. Oh, I got how many position? 1, 2, 3. I do get 3 position. So this become the reduced row echelon become 1, 0, negative 4, 0, 0, negative 4, 0, 0, and then 0, 1, negative 3, 0, 1, negative 3, 0, 0, and then 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0. So I have three prefix position 1, 2, 3. So yes, it span P2 because the vectors span R3, right? The sets span R3. It has three prefix position in 3 row, in all 3 rows. So you can get B in any way you want. The next one is about if this set form a basis for P3. So again, we change this set into, let's say this set is C. Write it in column form of the matrix. Oh, let's just write A then. So the first would be 5, negative 3. They're already in the correct orders for 2, right? And then the second one is 9, 1, 8, negative 6, right? 9, 1, 8, negative 6. The last one is 6, negative 2, 5, 0, because it's P3 means T to the cube, right? T cube. And then we have 0, 0, 0, 1. Okay, remember T cube is the last one. So T cube is the last one. So I want to know if it's a basis for P3, I would do the RREF. And hopefully by IMF, if it is become an identity matrix, I4, then it would be independent as well as span R4. And if it span R4, it would span P3. Okay, so I think I have enter 5, 3, 4, 2, 9, 1, just double check. 9, 1, 8, negative 6, 6, negative 2, 5, 0, 0, 6, negative 2, 5, 0, 0. Yeah. So I just need to do a reduced echelon of E, right? Oh, reduced echelon of E does not produce a identity matrix. So it's not, right? So it's not I4. So this is not a base. This is the vectors are not the independent. So not a basis. Actually, the values are 1, 0, 0 0.750, 0, 3 over 4, 0, 0, 1, 1 4, 0, 1, 1 4, 0, 0, 0, 1, 0, 0, 1, and then the last one is 0, 0. So we only have 3 vectors that are independent. The third one is actually a combination of the other one. The last one is about 3 vectors, and it is not a basis, but because of that, we still want to use it as a coordinate to see if what we can write for 3, 7. So meaning they are not a basis, but how can I write 3, negative 7 as a combination of them? So what you do is you just write it out and solve for like instead of PB, it would be PB times your XB equal to X, right? Equal to 3, negative 7 to solve it. And then you should have more than one equation. and you would write x3 equal to 0. I think one of them is a linear combination of the other, and then x3 equal to 1. You would have two solutions.